In this recap session, we will review the art of taking derivatives. In particular, we will cover basic derivatives, the multiplication rule, the derivative of a fraction, and the all-important chain rule. We will solve a few examples for each topic, and if you want more practice, I have several exercise videos for each topic. We start with the basic derivatives. These are the ones that you should know by heart because they will show up time and time again. Here are some of the usual suspects. The first one is the derivative of a power of x, where the power comes down in front of x and the exponent gets subtracted by 1. This of course extends to negative powers. The derivative of x to the power of minus 2 is equal to minus 2 times x to the power of minus 3. And thus this rule already eliminates the need to learn the derivative of 1 over x by heart, since 1 over x is simply x to the power of minus 1. And the same can be said for the derivative of the square root of x. By writing the square root as x to the power of 1/2, the resulting derivative becomes 1/2 times x to the power of minus 1/2. Next are the goniometric functions. Here you should remember that the derivative of the cosine of x is minus the sine of x, and conversely, the derivative of the sine of x is plus the cosine of x. The tricky part here is remembering which gives a minus sign and which does not. Another fascinating derivative is that of e to the power of x. This one simply returns itself again, e to the power of x. This means that the slope of the graph of this function will always be equal to the value of that function in that point. Now there are of course many more basic derivatives, such as the tangent of x. However, if you are proficient with the following rules, you don't need to learn these by heart, and I will show this for the tangent at the end of the video. The first important rule is to take the derivative of a product of two functions. It is crucial to remember that it is certainly not simply the product of the respective derivatives. Instead, it's the sum of two terms. First, leaving the first function untouched and deriving only the second one. And for the other term, you derive the first function and leave the second function untouched. For example, the derivative of x squared times the cosine of x is x squared times the derivative of the cosine plus the derivative of x squared times the cosine. Calculating each derivative, we get minus x squared times the sine of x plus 2x times the cosine of x. Now this rule can also be used to calculate the derivative of a fraction, so no need to memorize that complicated formula. Simply write the fraction as a product and then apply the product rule. Let's take for instance the derivative of sine of x over x, a clear fraction. However, we can write it as a product of sine of x times 1 over x. One product, two functions, so let's apply our rule. The first term becomes sine of x times the derivative of 1 over x. And the second term we get the derivative of sine of x times 1 over x. Computing the derivatives, we get minus sine of x over x squared plus the cosine of x over x. The last rule, and arguably the most important one, is the chain rule, and this one is used where functions are nested. Now let's skip the general expression for this one and go straight to some examples. Starting slow, we take the derivative to x of the sine of 2x. The way to think about the chain rule is to consider x being trapped inside various functions, and the way to get to it is to delve your way to it by taking derivatives along the way. Here we identify x being tied to this 2, and then 2x itself being trapped inside the sine function. Thus, we have two levels of entrapment here. To get to x, we first derive the sine while not caring what is inside of it, and then multiply this with the derivative of 2x. Deriving the sine gives us the cosine, and deriving 2x gives back simply 2. Now inside this cosine comes whatever was inside of the sine, and in this case that would be 2x, and this gives us our final result. Let's look at the derivative to x of 2 times e to the power of minus x squared, a Gaussian function. Here we identify that x is squared and multiplied by minus 1, but this minus x squared itself is encapsulated in this e power. Therefore, to get to x, we first need to derive this e power and then multiply with the derivative of minus x squared. Deriving an e power returns itself again. and the derivative of minus x squared is simply minus 2x. Again, don't forget that whatever was inside the encapsulating function needs to be copied, and in this case, the exponent of the e power remains minus x squared. To finish off, I have still to show that you don't need to memorize the derivative of the tangent of x. Using the product and the chain rule, it can be easily obtained. First, write the tangent as the sine over the cosine. Then write this fraction as a product of two functions. Now we can use the procedure of the product rule of derivatives. The first term becomes the sine of x times the derivative of 1 over cosine, and the second term the derivative of the sine of x times 1 over the cosine of x. Now to calculate the derivative of 1 over the cosine of x, we now use the chain rule. X is encapsulated in the cosine, and the cosine itself is encapsulated in the denominator of a fraction. Therefore, we first take the derivative of 1 over something and then multiply it with the derivative of the cosine of x. In the second term, we simply take the derivative of the sine of x. The derivative of 1 over something is minus 1 over that something squared, and in this case, that something is the cosine of x. And thus we get minus 1 over the cosine squared of x. The derivative of the cosine is minus the sine. Bringing it all together, we find that the derivative of the tangent of x is the tangent squared of x plus 1. And if this does not immediately ring a bell, try rewriting it using goniometric relations. And then we get that the derivative of the tangent of x is simply 1 over the cosine squared of x. Now, if you want more practice on derivatives, I have an entire series where we solve multiple exercises on all of these topics step by step. And as always, thanks for watching, and I will see you in the next one. Bye.